Welcome back to Dave Does Math from Home. This is part 3 of our video series on areas between curves, section 6.2. This is where the really cool stuff happens, so pay close attention to this. We're going to throw ourselves directly into another example and see what happens. I want to do y equals x minus 6, and the other function I want to look at is x equals y squared. So right away, hopefully we can tell that something is a little off because this function is not explicitly solved for y. This is, some would say, an implicit function. Or I guess it's implicit in terms of x, but that's not really how we write functions. This is unusual. If we solve this for y, we would get y equals plus or minus the square root of x. So technically it's not even really a function, because it doesn't pass the vertical line test. Each input is going to give me two outputs, a positive and a negative. But we can still find the area between it and this other function, and it's going to be exciting to do so. So as always, we're going to start by drawing a picture. My picture is going to look like this. This is x equals y squared, and y equals x minus 6. It'll look like this. Here's negative 6. This line has a slope of 1. I have an intersection point here, I have an intersection point here, and I am interested in this area. So, in the last example we did in the other video, we had an interesting situation where this area was sort of split into two pieces, and in quadrant 3, one of the functions was on top, and then that switched in the second part, and the other function was on top. This doesn't have that, really, but it kind of does with the bottom function. If we want to do this in the same way that we've done all of the other problems, we would slice it up into little vertical rectangles like this, and we would find the area of these rectangles by looking at the difference. We would say that the width of this rectangle is dx, and the height of this rectangle is the difference between the bottom and the top function. And we would do other rectangles over here. And we would find the areas of these other rectangles whose width is dx and whose height is the difference between the top minus the bottom. Here's the problem with doing it like this. In this function, or in this region, the function that is the bottom of the region switches about halfway through. Over here, the top is x equal y squared, or while we're doing it this way, let me write this as y equals square root x. On the left half of this area, the top function is the parabola, y equals square root x. The bottom function over here is also the parabola. This straight line is not involved with the left half of this function. Over here, the bottom is y equals negative square root x. We said that y equals plus or minus root x, so here's the top half, here's the bottom half. That's your top and bottom function for part of this. Straight through to here. To the left of this red line, you're going from the top of the parabola to the bottom of the parabola. To the right of the red line, that's when you're going from y equals x minus 6, the straight line, to the top of the parabola. So it switches halfway. And we could do this. We could find the x values of this point, and we could find the x value of this point, and we could find, I guess the x value of this is pretty obviously 0. But we can find these three x values, and we could do this problem using two separate integrals. One that goes from x equals 0 to x equals red line point of positive parabola minus negative parabola, plus the integral from red line to this other point of parabola minus linear function. That is a thing that we could do. That is a thing that I do not want to do. That's a lot of work. And fortunately for us, there's a much easier way to do this problem. It involves a bit of a paradigm shift, which is why it gets its entire own video. But it's a really, really important paradigm shift to have. It's going to be crucial for going into the next two sections of this chapter, 6.2 and 6.3. So bear with me, and let's see what it's about. I'm going to redraw this with less clutter and with a fresh marker. Okay. So that whole discussion started with if we do this in the traditional way. And the traditional way, by traditional way I meant vertical slices, where you have rectangles that go from the top to the bottom with a width of dx. Here's what I'm going to suggest we do for this problem instead. I want to do horizontal slices. So I want to slice this up like this. I want to look at this rectangle. Or down here would be this rectangle. Or up here would be this rectangle. So instead of slicing this thing vertically into little strips that switch right here from having a lower border of the parabola to the lower border of this linear function, instead of doing it vertically, I'm going to do it horizontally. And before we get into this, we have to talk about what these horizontal slices mean. The vertical slices had a height that was the difference between the top and the bottom function. That's how we defined the height of those rectangles. And the width of those rectangles was dx. Here, when we look at this rectangle, hopefully we can see that this height, or I guess width in this case, is the difference between the right function minus the left function. So we're using horizontal distances instead of a vertical distance. The right and the left are going to be, or I should back up a little bit. When we do these horizontal distances, we're looking at we're comparing two different y values. Like in the very first example we did for this section, when we did the area between x squared and square root x, we were looking at the top function being y equals root x and the bottom function being y equals x squared. So we were comparing this y value with this y value, two different y values, two different heights, to get the difference in height. So that's where this square root x minus x squared, that's the difference in the height between those two things, because this is a y value and that's a different y value. So the first transition we need to make, if we're going to slice this thing horizontally instead of vertically, the first sort of cognitive shift we have to make here is to think about this not in terms of top and bottom, but we need to think about this in terms of left and right. So here we have the right function, and the right function is always going to be y equals x minus 6, but this isn't going to work for us. If I'm thinking about this in terms of right and left, I need to transform this into an x equals function, because right and left are x values, and the difference between right and left has to be the difference between one x value minus another x value. So this x value, if I add 6 to both sides of this equation, I can express this function as x equals y plus 6. Now, this thing in terms of y isn't going to work. Now it's in terms of x, then this will work as my rightmost y value. So on the right, and the nice thing about slicing this horizontally is that that's always the right y value. I don't have to switch halfway through this integral from one thing to the next, like we did when we were cutting it vertically. It's always, the rightmost y value is always this linear function, x equals y plus 6. So this is x1, that's the rightmost y value, that's what we're going to use. The leftmost y value is always going to be this parabola, and that is already in terms of x. That's x equals y squared. So that's going to be x2. That's our left value. And so I've already got the right and left sorted. So that's cognitive shift number 1. You can transform these functions into functions x equals function of y, and then do this horizontally instead. That's one dimension of these rectangles. We need to talk about the other dimension of this rectangle. So we've got the lateral direction covered, that's right minus left. We need to talk about the vertical direction, or the vertical dimension of these rectangles. The vertical dimension is the part that we're going to slice pretty much infinitely thin. When we did this in the normal vertical rectangle situation, that infinitely thin dimension is what we call dx. That was our infinitely thin little strip of the x-axis. So here, if we're doing it horizontally, we're going to call that, this distance here, the vertical dimension of this, we're going to call that dy. So, the size of each of these rectangles, we don't need this anymore. The size of each of these rectangles is going to be the right function, which is y plus 6, minus the left function, which is y squared. This is the horizontal dimension. The vertical dimension is going to be dy. And this is going to help us out a lot. If you're going to do it with a dy, if you're going to slice it horizontally and get infinitely thin strips of the y-axis as one of your dimensions here, all of these variables have to be y's. You can't integrate a function of x's with respect to y. If this is a y, all of these have to be y's. If this is an x, all of these have to be x's. You can't mix and match. You can mix and match when we get to Calc 3, but that's a completely different situation that has very little to do with this. For now, you cannot mix and match. If you've got a dy, only y's. If you've got a dx, only x's. There's no fraternization between the x's and y's here. We're very exclusory? Exclusory, is that a word? I'm making up words. Okay. My wife is telling me that it's exclusive. We're very exclusive here. That makes sense. I knew exclusive was a word. I was trying to make up words. I didn't get away with it this time. I don't know. So, we have the right minus left settled. Right now, there's only one thing that we have left to do, and that is we need to find these intersection points. This is going to be a y value, and this right here is going to give us another y value. And for this part, we're going to set these two things equal to each other exactly like we have in the past, except this time we're going to set the x values equal to each other. So we're going to have, I'm going to come over here to do this. We're going to have y plus 6, that's one of our x values. We're going to set that equal to y squared, that's our other x value. This is what we have to solve for. And when we solve this, we're going to get y values, which is exactly what we want. We're integrating functions of y with respect to y, so we need the bounds to also be y. Don't plug in the x values of these coordinates, that won't help you. we need to use the y value of the coordinates because everything is y's now. So I'm going to subtract x plus 6 or y plus 6 from both sides to get y squared minus y minus 6, which is y minus 3 times y plus 2. So y is going to be negative 2 and positive 3. So this is the integral that I'm working with. Again, if you need to stare at this for a bit longer, pause the video or take a screenshot because I'm about to erase it. Okay, this is the integral that I'm working with here. These are the bounds on the integral. Once I figure this out, I'll have my values. And I got to do it fast. We're already at 16 minutes here. Wow, talked about this for a while. Okay, so a is going to equal y squared over 2 plus 6y minus y cubed over 3 from negative 2 to 3, which is 3 squared over 2 plus 6 times 3 minus 3 cubed over 3 minus, big brackets, negative 2 squared over 2 plus 6 times negative 2 minus negative 2 cubed over 3. That's our area. I could probably figure this out without a calculator. I just don't want to, and I'm running out of time on this video anyway. If I don't finish this in like less than 17 and a half minutes, the camera just automatically truncates it and starts another video because the file formatting on the SD card is terrible. So I'm going to end it here. If you want to find out what this number is, use a calculator. Godspeed. If you don't want to find out what this number is, that's fine. If this were a test problem and I got to here, this would be 9 points out of 10. We have successfully sliced it, we set up the right integral, we integrated correctly, we plugged in the numbers, and we got bored of the arithmetic and we gave up. That's fine. The arithmetic is absolutely the least important part of this. I'm interested in the calculus, and we got the calculus down pretty well. That's it for this one.